Okay, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. We're in the middle of some examples last time, so let's get back into it. Make sure I can see the chat here. Okay. All right. Cool. Yeah, this was from yesterday. We were doing a bunch of counting examples. We did from 4 onwards, and we did a lot of spoke about how we would go about getting to the answer, how we would structure the answer, how we would figure out what to do to get the answer. We used this kind of idea many times, the idea where we wrote down a bunch of slots and we figured out how many choices we can have for each slot, where we imagine the stage as these little things that we can fill in. Did it here again, and did it here again, did it here. Like we use that a lot, right? So what we're going to do now is I want to finish up this problem here, problem 8. And I also want to show you some other ways that we can visualize things. Besides, I did show some other ways before as well. When was that? No, it wasn't that far. It was like maybe the one right before. Yeah, so like you can do this like little table here. I'm going to show you how to do other tables as well. But that's what we're going to do. And we will start probability on Friday. So yeah, that's it. Let's actually just jump in. Like last time, what we're going to do is I'm going to put the blue numbers represent choices. Okay, so let's read this problem. 10 balls are labeled 1 through 10. You put them in a box, you shake them up, and you pick out 5 at random. After each pick, you do not replace the ball before picking again. This is called sampling without replacement. That is actually very important. Okay. How many possible scenarios are there of this kind? 1, where the second of the 5 numbers drawn is an 8, right? So no matter how you draw them, you can get a 5, then an 8, then a 7, then a 3, then a 2, right? But whatever, the 8 is going to be the second position. Or B, the second of the 5 numbers drawn is larger than the first number drawn, right? So we're going to count how many ways these things can happen. Okay? So give you guys a chance to kind of, you guys should have this question written down already, actually. Or saved somewhere in your notes. So let's actually do that. A. This just seems, I don't know, I'll probably stick with it. I like how this. All right, so what we can do is we can visualize the 5 numbers that we're going to pick. You can assume we're picking them one by one. So I pick the first number, the second number, the third number, the fourth number, the 5th number. And we know that the second number needs to be an 8, right? So this accounts for one choice being made for us. It has to be an 8 chosen in the second position. Now, how many numbers can I choose to put in the first position? Oh, is anyone there? Like there has to be an 8 in the second position. How many choices would I have for the first position?
Is it 10?
Why would it be 10? What are you thinking here?
Because there are 10 balls in total, so like the
Right,
likeliness.
but here we're sampling without replacement. You see that?
Yeah.
What that means is once we pick a ball, it's not in the box anymore for us to pick again. Right? So once one ball is picked, you no longer have 10 balls to pick from.
Mm-hmm.
Right? So if I already picked an 8 and put it in the second position, how many possibilities do I have for the first position?
9.
Now I have 9 left, right? So, and then how many possibilities for the third position? Well, at this point, I picked 2 of them, right? So I picked one of the 9 to put in the first position. I know there's an 8 in the second position. So there are now 2 balls already picked. And then I have to pick out of a box of how many remaining. Well, there are 8 remaining. Once I pick out that one, I don't replace it. So now I have 7 remaining to choose from. Once I pick out that one, I now have 6 remaining to choose from.
Wait, so why is there an 8 in the third one? I'm confused.
Because this is the first pick, second pick, third pick.
No, I know, but how could you get 8 twice?
Remember, the blue numbers represent the choices, right? The 8 here is not a choice. The 8
I see.
Actual thing. So instead of 8, the blue number here is the 1.
I see. Okay, thank you.
Right. So the blue number is the number of choices I have. So there's an 8 specifically in the second thing, right? Which is, it accounts for 1 choice. Whereas the blue numbers is the number of options I have left. So I know if I have an 8 in the second position, I have 9 other options to put in the first position. Once I fill the first position, I would have 8 other options to put in the third, and so on. Right? So these are the choices here. These are the choices. Okay. So now I start counting them by the multiplication rule. You would have, well, 9 times 1 times 8 times 7 times 6 total choices, which is 30, 24. There's another way you could think about this. Another way to think about this. Is to, we have 10 balls. 1 choice is made for us. Now we have 9 options left. We must choose 4 of these 9 options to put in order. And it's without replacement. i.e., no repetition. Okay. So look at what we actually have. Someone picked the number 8 and put that in the second position. Now we have 4 positions to fill, and we have 9 options over there to fill it with. Now we're going to fill it in such a way that there are no repeats that are occurring. And we're also going to actually fill it in such a way it's like I'm picking one after the other, and the balls are numbered. There's an inherent kind of order here in the way I'm picking the balls. So now it's a matter of, I have 9 objects. I want to choose 4 of them in some order without repeat. What do we know can count something of that situation? What does that sound like to you? So there's a particular kind of object that we know that can count something like that specifically in one shot. We have 9 options, must choose 4 in order, no repetition. There's a bunch of key phrases here, and they should all indicate one thing, really.
Is it a permutation?
It's the permutation. The answer would be P of 9, 4 choices. And so we actually know that P of 9, 4, you can actually put it in your calculator, is 3024. It's actually also exactly equal to 9 times 8 times 7 times 6. Right. So you could do it this way, count your choices one by one, do the multiplication rule. You could also think of it this way and understand that, oh, what I'm actually doing is, because one option is picked for me, I'm choosing 4 more options out of 9 possible options where I can't have repeats, and there's an inherent order. There's a first thing I picked, and a second thing I picked, and a third thing I picked, and a fourth thing I picked, right? And so, yeah, a permutation can count this without any fancy diagram or anything. Okay. Let's move on to B. So in B, we want to pick these numbers in such a way so that the second of the 5 numbers drawn is larger than the first. Okay, so we want the number in the second position to be bigger than the number in the first position. Larger. Okay, so there's one thing we can note here. Note we can not have 1 in the second position. Right, so that should be the first thing you should note. If the second number has to be bigger than the first, 1 cannot be in the second position because 1 is the smallest number. There is no other number that is smaller than 1. So 1 could never be bigger than the first. 1 is the first. The 1 is the lowest number. So it's not possible to have a 1. So the second position has to be, so the second position must be 2 or 3 or, well, anything really, all the way up to 10. And it will be possible to pick a number that is smaller than all of these guys, right? So now knowing that, I'm going to start visualizing this. Again, we have our 5 slots, 1, 2, 3, 4, 5. So I could have a 2 in the second position. How many choices would I have for the first position? Well, only one choice really, specifically the number 1 itself. Right? Now, once I've done that, 2 numbers chosen. Now, 8 remaining. must choose 3 in order without replacement. Okay, so now I would have 8 choices what to put here, 7 choices what to put here, 6 choices what to put here, right? So this would be, well, 1 times 8 times 7 times 6 total choices by multiplication rule. So that's the number of ways to have a 2 in the second position and for the second number to be bigger than the first. But that's not the only option, right? I could have 2, 3, 4, 5. I could have a 3 in the second position, or a 4, or 5, or a 6, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? So I could have a 4 in this location, or I could have a 5 in this location, or I could have a 6 in this location, or I could have a 7 in this location, or an 8 in this location, or a 9 in this location. One more, 1, 2, 3, 4, 5, or a 10 in this location. Okay, now let's go back and start counting these. If there's a 3 in the second position, how many options do I have for the first position? What would you guys say? So there's a 3 in my second position. How many numbers can I put in the first? Are you guys hearing me? Are you guys there? Any ideas?
It would have to be a 1 or a 2.
It would have to be a 1 or a 2. So how many choices is that?
2.
There are 2. There are 2 possible things that I could put in the first position. Now, after filling the first and second position, that means I now have 8 things in the box that I can put in the third, fourth, and fifth position, which I don't have to worry about how they relate to the others. So this is, again, going to be 8, 7, 6. Similarly, if there's a 4 in the second position, there must be 3 possibilities that I can put in the first. Once those 2 are chosen, 8, 7, 6 again. Similarly, I could have 4, 5, 6, 7, 8, or 9 options here. And then once those 2 are chosen, I have 8, 7, 6 options for the others. Right? So now you can go and you realize, oh, this is going to be 2 times 8 times 7 times 6. And this one is going to be 3 times 8 times 7 times 6. And so on. Going all the way down to 9 times 8 times 7 times 6. And then what we would do is we would add these since no overlap. We spoke about that last time. So what we would have is we add up all these numbers. So we have a 1 times an 8 times a 7 times a 6, plus a 2 times an 8 times a 7 times a 6, plus going all the way down to 9 times an 8 times a 7 times a 6. You'll notice here that the 876, you could plug this in your calculator if you want to plug in the 10 things, but we can make this a little bit nicer on or easier on ourselves by realizing that 876 is a common term. You could factor it out. And then we would be left over with 1 plus 2 plus 3 plus all the way up to 9. So that's the sum of the first 9 positive integers. We actually have a formula for this. When I was deriving the sinking fund formula, and I told you that story about baby Gauss, how he added up the numbers from 1 to 1,000. So there's a nice little formula for that. It's going to be 9 times 9 plus 1 all over 2. 2 would cancel into that, goes 4. So we would get 4 times 7 times 6 times 9 times 10. And that would be 15,120. Which you could have plugged that into your calculator from here and do it, but I'd rather plug in these than like a whole list of 10 things where I'm going to probably punch the wrong number at some point, right? Like if I'm adding up 10 numbers where each of them is a product of 4 numbers. I mean, I'm doing that in a test. I would think that, I mean, the likelihood of making a mistake and punching something wrong on my calculator would be, you know. So whatever. At the end of the day, you should get 15,120. There are 15,120 ways to choose 5 balls out of 10 balls in order without replacement in such a way that the number on the second ball is larger than the first, right? These are not something that you'd want to list out all of them, obviously, right? You'll take forever to actually count them one by one. But with this process, we can count them. Yeah, and that's 8. I think I just started writing larger and larger and larger as time goes on. Oh well, whatever. Yeah, so that was the last problem. So we're going to move on to more visualizations, a definition, and then I let you guys go, I think. Okay, so let's talk about that. Other ways to visualize processes. I want to talk about 2 main ones. We're going to look at tables, and we're going to look at tree diagrams. And to illustrate using these, I'm going to both we'll go back to an old probability teaser example. So we did this example where we toss a fair coin 3 times. What is the probability? We get 2 heads. So we actually know the answer already. I did that with you. It was 3 out of 8. That was the probability. Okay. So before, how we would have visualized this, we've done the slots, toss 1, toss 2, toss 3. Realize that there were 2 choices here, 2 choices here, 2 choices here. That leads to 2 cubed equals 8 total choices. Okay. And then we had to figure out, well, how many of those choices is the one that we want, right? So then we go into figuring that out. So we could say, if 2 tosses must be H, then 1, or exactly 1 must be tails. There are 3 no, let's see that 2 cubed equals 8. There are 3 possible positions to put the T in. So you get the probability of 2 heads to be equal to, well, 3 out of 8. There were 8 total possibilities. There are 3 possible ways to have 2 heads. It was easier to count where the tail had to be, because there was now 1 tail that I had to keep track of. So I wouldn't have to keep track of 2 heads, but you could have done that as well, like a head in the first and the second position, or a head in the first and the third, or the second and the third. You'd still have 3 positions if you counted that way. It was just easier to count where I put the T instead of where I'm putting 2 H's. Easier to place 1 thing than 2 things. So yeah, we'd get 3 out of 8 that way. That's how we would have done it before. Now I want to show you 2 other ways to do it, because there's more than one way to skin a cat, and in certain problems, certain situations, one method might jump out to someone more than another. Okay, so now let's use tables. Okay, so here's how the table situation is going to work. So I'm going to tell you a general way to construct a table in a very specific situation, and then I'm going to do it, and then I'm going to answer the question with it. So suppose we have an experiment with R stages, and each stage has n possible outcomes. More specifically, the same n outcomes. Okay. Then the multiplication rule tells us that there are n to the r total options. And we may place them in a table where the options alternated as described. Now, I'm going to give you the very general way to do it, but then I'm going to do it specifically for this example, and you'll see what I'm talking about. You'll probably be a little confused when I'm describing it in general, but when you see what I'm talking about, and then you think about some other situation, maybe there was a dice with 4 sides. How would you actually figure out how to draw the table for that? You're going to know now. So you would have the table like so. Okay. So now there would be R columns, and there would be N to the R rows. And what we're going to do now is we're going to alternate each option every blank rows, where blank is represented by the number I'm going to put over here. So you would alternate every n on iPad, every n to the 0 rows, which is literally every other row. You'll alternate through all the options. Then every n to the 1 rows, every n to the 2 rows, every n to the blah, blah, blah rows, and until you get n to the R minus 1, right? So you'd have R rows by doing that, R columns by doing that, right? And this just tells you how often you alternate after every row, right? You're going to see what this means when I actually do it. So, for example, here, for this example, the coins, right? Notice what we have. We have R equals 3 because there are 3 coin tosses. So you can think of this as one toss is a stage, and n equals 2. So this is like heads or tails. So we have R equals 3. Let's put stages in here. We have R equals 3 stages and n equals 3 options per stage. Okay. We also know that table must have n to the R equals 2 cubed equals 8 rows. And so now you go and you construct a table that does that. It must have R columns and 8 rows. So 1, 2, 3, 4, 5, 6, 7, 8. So we're going to have this being toss 1, toss 2, toss 3. Okay. And we're going to alternate every 2 to the 0, or 2 to the 1, or 2 to the 2. Okay. Now, what do I actually mean by that? You go through all the options and you alternate every other row, every one row, right? So we had 2 options, heads or tails. You're literally going to fill out this table by alternating heads and tails, one row after another. Heads, tails, heads, tails, heads, tails, heads, tails, right? Now for the second column, you're going to alternate every 2 rows, every 2 to the 1 rows. So I would go heads, heads, tails, tails, heads, heads, tails, tails, right? For the third column, I would alternate every 2 to the 2 rows, which is every 4 rows. Heads, 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 tails, 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 tails. I do that for n to the r rows. And what you'll notice here is that this is all possibilities. You'll notice the number of rows, each row is a possibility. So there are 2 cubed equals 8 total possibilities. Okay. So now what you can do is you can actually now pick out the, someone got kicked out of the room just now. Now what you can do is you can actually pick out the things you want. So we wanted 2 heads, for example. So where can I get 2 heads? Well, the second row has 2 heads. The third row has 2 heads. Fifth row has 2 heads. Notice that there's 3 situations that you can get 2 heads. 3 possibilities. For 2 heads, right? So I can get 2 heads here. I can get 2 heads here. I can get 2 heads here. So notice now that, so the probability of 2 heads, well, that's going to equal to, well, there are 3 possible scenarios out of 8 possible scenarios that I could get it, right? And the benefit of doing the table is that it actually gives you a lot of detail. You can know exactly what each stage, what things happen in which order, right? And you're never going to worry about, oh, did I count all of them? Did I get all the positions where the H was in the second position or the third? Like you won't have to worry about forgetting something. If you fill out a table according to this pattern, you will hit all possibilities, right? So, yeah. So similarly, if I had something where it had 3 options, say A, B, C, then I would go A, B, C, A, B, C, A, B, C. Then alternate every 3, A, B, 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 C, C, C. Then alternate every 9, A, B, 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 C, 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 C. And you keep going for as many stages as you have, right? And that's how, and you hit all possibilities by doing this. So that's one situation. Another thing, it's one way to visualize it. Another way to visualize it is with what we call tree diagrams. Okay, so let's look at the same example, but doing it with something called a tree diagram, which is a different way to visualize something. So here, your stages are, again, kind of like columns. Stage 1, stage 2, stage 3, representing toss 1, toss 2, toss 3. And so these guys are all like over there. And so here it's like time before experiment starts. And then there is a singularity, the beginning. So this represents the start of the experiment. Experiment starts here. Okay. So now you go through and you kind of fill out all possibilities. Well, okay, I'm going to start the experiment. What are the options? What are the things that could happen? Well, I could get heads or tails. Okay, so now what happens is there are two possible starting points for the stage 2. Now I don't necessarily know which one is going to happen, but I know if I got heads first, there are again two possibilities for what can happen. Heads or tails again. If I have a tails, then I will again have two possibilities for what can happen. Heads or tails. Now, for the third stage, again, this branches off into two things. Heads or tails. This branches off into two things. Heads or tails. This branches off into two things. Heads or tails. This branches off into two things. Heads or tails. Right? So now, again, you'll notice that there are 8 possible ways to end up. 8 possible outcomes for the experiment. Right? And each arm is representing the experiment. So if you start to talk about the number of ways to get what we want, and remember, we want 2 heads. So we can get head, head, tails. Or we can get head, tail, head. Or we can get tail, heads, heads. Right? Again, 3 ways to get 2 heads. And so again, probability of 2 heads is going to be 3 out of 8. Right? What I want you to notice here is that each arm represents a possibility. Each arm in the tree represents a possible outcome of the experiment. And moreover, to find the probability of some outcome, one of the arms occurring, you can multiply the probabilities along each stage. More on this later. So for example, what is the probability that I get heads, 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 right? Well, the probability is a half here, half here, half here. Multiply half by half by half, I get 1/8. That's actually the probability of getting head, head, head. That's basically what I was saying. But we'll talk about that more later. And here, each node, which is this guy, represents a possible starting point of a stage. Okay, so that's that. So that's tree diagrams, and that's using tables, and that's how you would construct them. Make sure you don't miss anything. And you can count along arms. Of course, here, when you count along the probability of each arm, you'd add each arm together because they're mutually exclusive. We'll talk about that later. Don't worry about it right now. There is just an important fact I want to remind you of. Fact to recall. There is a definition that I gave you a while ago, I think. I feel like I forgot to mention it in one of the classes, but I don't remember which one. So I want to recall it. Let A, B be sets. We say A and B are disjoint if the intersection is the empty set, right? So two sets are disjoint if they have no intersection. You can have, they're completely separate with no overlap, right? So that's what disjoint means. I just want you to remember that. Disjoint means no overlap. Yeah, we'll stop right there. We'll start probability next class. Be somewhat of a whirlwind because again, I'm going to have to give you a bunch of definitions to start off. Make sure that we know probability right because it can be a little bit tricky if you don't follow certain protocols. So I'm going to be very careful in how I set out those protocols and those definitions to make sure that we know how to do them. Yeah. Okay. From small to large. All right, so that being said, we will stop right there. Yeah. Without further ado, I will see you guys on Friday. Enjoy the rest of your day. I will see you guys in the next one. Ciao.